prove two results related to derivatives, which are of course useful and interesting in their own right, but will also be used in subsequent developments of this chapter. Okay, the first of these is called the intermediate value theorem for derivatives. So let me write the statement first. Okay, the statement is as follows. Say the function f is differentiable over an open interval of the form AB if a is less than x1, which is less than x2, which is less than b, and c lies between the derivative of f at x1 and the derivative of f at x2. Okay, so x1 and x2 are just 2 points on this interval a to b, and let's say that their derivatives take different values. So f prime x1 is different from f prime x2, and so c is some value that lies between these two. Then there exists, let's say, x between x1 and x2 such that f prime x is equal to c. Okay, so now you see why this result is called an intermediate value theorem for the derivative, because it exactly shows that the function is differentiable between a and b. Now f prime x1 and f prime x2 are two values that are attained by the derivative. C is a value that lies between these two, and we are saying that that value c is also attained. In other words, there exists a point x between x1 and x2 where the derivative is in fact exactly equal to c. In other words, intermediate values of the derivative are actually attained. Okay, so there are a couple of things to note about the statement before we get into the proof. The first is that the derivative of a continuous, we know that continuous functions satisfy the intermediate value property, right? If you have any continuous function, then all values between two values attained by the function are attained, right? So what this result is telling you is that the derivative of a differentiable function also satisfies this intermediate value property. However, this is notably, different because the derivative of a function need not itself be continuous, right? So even though the derivative is not necessarily continuous, it satisfies this intermediate value property, right? Which is what makes this very surprising. So in particular, the derivative of a differentiable function, or the differentiable part is implicit, the derivative of a function need not be continuous. In other words, derivative satisfies an intermediate value property spite right? So derivatives are interesting in that manner, right? So there is some structure that you know about a function from just the fact that it is the derivative of something else, right? So it need not be continuous, but it satisfies the intermediate value property. Okay, so I leave it for you to actually come up with examples of this kind. An easy search on Wikipedia or on Google will show you examples of differentiable functions whose derivative is in fact not continuous, right? And go back and check in those examples that the intermediate value property still remains satisfied. Okay, another thing to note, which is also a consequence of this theorem, is that therefore the derivative of function cannot have a type 1 discontinuity. Right? So in other words, the derivative of a function cannot look like this. So we know what type 1 discontinuities look like. So there is some left limit. Let's say there's a function value, and maybe in this example the right limit matches the function value. Okay, so these kind of thing, a derivative cannot look like this. Why? Well, because if it did, then it would violate the intermediate value property, right? There are values out here that your derivative would not be attaining, which would violate the theorem that we've just written. Okay, so with all this commentary, now let's get down to the proof. The proof is actually, remarkably elementary. So let g be the function g of x is equal to f of x minus c times x, where c, recall, is the intermediate value between f prime x1 and f prime x2. Okay, so the first thing we note and let's assume without loss of generality, assume that f prime x1 is less than f prime x2. Okay, had the inequality been reversed, then nothing really changes. You can just multiply f by minus f if need be and make this get satisfied, right? So this is without loss of generality. Now, by this convention that the derivative at x1 is less than the derivative at x2, check that in fact the derivative of g at x1 is in fact negative, right? Because it's c must be larger than f prime x1, and so g prime x1 is negative. And moreover, g prime x2 must be positive. Okay, now g being a continuous function in the interval from x1 to x2 implies that it must attain its minimum, right? Since g is continuous on the interval between x1 and x2, it must attain minimum, right? And then I leave it to you as an exercise to check that because g prime x1 is less than 0 implies that x1 is not the minimum. Why is that? Well, the fact that the derivative is 0 implies by the definition of the derivative that at x sufficiently close to x1 but to the right, g of x minus g prime x must in fact be negative, which means that the function should be decreasing in an immediate neighborhood around x1. And analogous reasoning also tells you that g prime x2 being positive implies that x2 is not the minimum. Right? Patching these together, you know that there exists some x between x1 and x2 where g is minimum. And this implies that in fact at this particular point x, you must have g prime x is equal to 0. And you can convince yourself that g prime x equals 0 is exactly the condition we were looking for, because at that x, if g prime is equal to 0, that would imply that f prime is equal to c. Okay, so elementary result, this basically proves that the derivative of a function satisfies the intermediate value property. Okay, there's one more result that we need to do. This is actually called a generalized mean value theorem. So we've just proved the mean value theorem already. This is just going to be an elementary generalization of that statement. Let f and g be continuous functions on AB. The same hypothesis as the original mean value theorem. Differentiable on the open interval AB. Okay, then there exists an x between A and B such that the following condition is satisfied. F prime x times okay, so under the same hypothesis as you have under for the original mean value theorem, that is your f, but I have two functions now satisfying that hypothesis. F and g are continuous on the closed interval from A to B and differentiable in the open interval from A to B. Then you are guaranteed that there exists at least one x in the open interval from A to B, that is between A and B, which satisfies the condition that f prime x into g of B minus g of A is equal to g prime x into f of B minus f of A. Okay, so if you take g of x is equal to x, then convince yourself that this is in fact the same classical mean value theorem. Right, so in that sense, this is a generalization of the mean value theorem. However, you will see that just as the mean value theorem was a trivial consequence of Rolle's theorem, so is this generalization of the mean value theorem. Okay, so the proof is actually going to be very straightforward. So let me now define the new function h as follows. H of x is equal to f of x times g of b minus g of a minus g of x okay, so define this function h like this. You see that h of a, well, substitute x equals a in this. With a little bit of algebra, you should be able to see that h of a is equal to f of a times g of b minus g of a times f of b. Right? Similarly, I leave it to you to check that h of b is in fact also the same thing. F of a times g of b minus g of a times f of b, which is h of a. Okay, both of these in fact are consequences of the definition of h. Now, therefore, since the function h takes identical values at the endpoints a and b, by Rolle's theorem, there must exist an x between the two where the derivative is 0. By Rolle's theorem, there exists an x between a and b such that h prime x is equal to 0. And the point where the derivative of h is 0 is in fact the same as the point that we want in order to prove the generalized mean value theorem, right? So this completes the proof. Okay, so these are the two results that I wanted to cover in this video. In the next, we will prove the famous L'Hopital's rule.